Right, so now we get on to the solving equations, right? And the thing about solving logarithmic and exponential equations is there's a reason why they're in the same chapter, because we use one to solve the other. They're inverses of each other. And this is kind of a function which is called transcendental. It's something you can't solve these things by just adding and subtracting things to both sides. That would be algebraic, right? This is transcendental. The only way we're going to get at what's inside one of these functions is by using its inverse. Now we know what the inverse is. Okay, so let's see. There are simple equations, meaning for the most part that means one-to-one, something we've seen. And then there's the ones where we actually have to get out our inverse properties. So the first rule is if it looks like it could be solved with one-to-one, you should solve with one-to-one. Right? And what we mean again by one-to-one, for exponentials, one-to-one means you can write it like 2 to the x equals 32 can be written as 2 to the x equals 2 to the fifth, because 32 equals 2 to the fifth. And then because we have an exponential equals an exponential, and the bases are the same, it must be that the exponents are the same. Right? So the goal is just write it so that both sides are powers of the same base. And then you have an equation in the exponents. X equals 5. X equals 5. Right? The letter B is not written as a one-to-one, but if you add the log 3 to both sides, then it is. Right? So same thing with logarithms. If you can make it a logarithm equals a logarithm, and they both have the same bases, then it must be that what's inside, the arguments, are the same. So ln of x equals ln of 3, then make an equation out of what's inside, x equals 3. One-to-one property. Sometimes the one-to-one property, you got to like do a little bit of manipulating to make it look like that. This one here, 1/3 to the x equals 9, right? You got to be able to see that both sides could be represented as powers of the same base. And when you see 3 and 9 in the same equation, the base is going to be 3, because 9 is 3 squared, right? Now, the harder part is, how do you write 1/3 as a power of 3? Well, remember, properties of exponents. 3 to the negative 1 is 1 over 3 to the first, right? It flips to the other side of the fraction. So 1 over 3, right, like this. 1 over 3 equals 3 to the negative 1. And then we had a power of x here, so if I raise that to the x and raise that to the x. And then how do we simplify when we raise a power to a power? We multiply. Negative 1 times x, that's where this 3 to the negative x comes from. So now since 3 to the negative x equals 3 squared, since the bases are the same, then the exponents are the same. Let me see if I can fix this thing because it's causing me trouble. Okay. Okay, so if you can solve it by one-to-one, solve by one-to-one. But what we're really interested in most of this is how do we use logarithms and exponentials to solve each other. Right? These are the basic steps if you want to write them down. So in both cases, you start by isolating, right? Isolating meaning make sure that the exponential is the only thing on that side of the equal sign, or make sure that the logarithm is the only thing on that side of the equal sign. And in some respect, and you'll see in a minute, then we use the other function. For exponentials, then we take the log of both sides. For logarithms, we convert to an exponential. Now, there's an extra step when it comes to logarithms, because if you remember, logarithms, the graph of a logarithm looks like this. Remember, it has an asymptote on the y-axis, and the domain is x greater than 0, which means sometimes if you solve and you get something that when you check it, it actually leads to the logarithm of 0 or a negative number, then you've got to throw it out as extraneous. Right? We've seen that before. We've seen that with radicals. We've seen that with absolute values. That can happen. So we're going to do some examples of each, and then we'll go through the exceptions, the things that are a little bit different. So here, this is an exponential equation, right? It's not a one-to-one. First step would tell you to do what? The list I just gave you, the first step of solving an exponential is isolate. What do you have to do to this problem to isolate? I mean, the exponential is 5 to the x. What do you have to move? The 2, right? So how are you going to do that? How about a divide? So 5 to the x equals 16. Okay, that was the first step. We isolated. Second step would tell you to take logarithms both sides, okay? Which logarithms? Because now you've got options. Okay, the strategy is generally, I'm going to show you 2 different ways, but the strategy is generally take the logarithm of the same base as the exponential. So take logarithm base 5 of both sides. Right, so that'll make this one look like this. Log base 5 of 5 to the x equals log base 5 of 16. Now remember the properties of exponents. We actually just used this going over the homework. Is it still up there? No. When the base of the logarithm matches the base of the exponential, they cancel each other out. And it all simplifies to the exponent. Right? That's how we're solving for the x. Right? That isolates the x all at one time. Okay. So that equals log base 5 of 16. Now, at this point, this is where change of base formula can come in. Right? So how could I rewrite log base 5 of 16 using change of base so that it's common log or ln? Log, I'll use common log. Log of 16 over the log of 5. And you just have to turn that into a decimal. Clear. Log 16 in parentheses divided by log of 5. 1.723. Now, if you, instead of taking log base 5, let's just say you take log base 10. At the very beginning, just take log base 10. Right? Then we would have it look like this. Log base 10, log of 5 to the x equals log of 16. And these are our log base 10. Okay, now use the power property to get that x out of the exponent and down to the level where you can solve for it. Right? What will that look like if I use the power property? X log 5 equals log 16. And then solve for x by dividing by the log of 5. Right, so the log 5 cancels, and x equals the same thing that it did over here, right? Log of 16 over the log of 5. So it doesn't matter which way you would want to go with it. You know, one of them you end up using the property that is basically about inverses. The other one you're using the property about power property. In the end, you get the same calculation. Good. Okay, what do we need to do to isolate this exponential? Add 7 to both sides. E to the x equals 30. Okay, that was the first step. Second step is take a log of both sides, right? Which log? Well, if you're going to match the base of the exponential with the base of the logarithm, it's ln, right? ln. So do ln of e equals ln of 30. And then how does the left-hand side simplify? ln of e to the x equals x, right? The base of e matches with the base of e, so it all simplifies to the exponent. So put that in the calculator. 3.401. Okay, let's try another one. Okay, a little bit more going on in this one. What all do I have to get rid of here so that I've isolated the exponential? The 6 and the 4. Which one should I get rid of first? The 4, right? Could you get rid of the 6 first? Sure. You could divide by 6 as long as you divide here, here, and here, right? Then you'd still be right. Most of the time we don't think of that. We just divide here and we divide there and we forget about the 4. So basically, if this was an equation like 6x plus 4 equals 11, there's no question what you would have done first. You would have subtracted the 4. So you need to subtract the 4. So that'll be minus 4, minus 4. 6 times 2 to the t plus 5. That was not good. Undo. Equals 7. Okay, then what? Divide by the 6. So that'll be 2 to the t plus 5 equals 7 over 6. Okay, next. Take logarithm both sides. Which logarithm? Base 2, right? Match the base of the logarithm with the base of the exponential. So log base 2 of 2 to the t plus 5 equals log base 2 of 7/6. And I would not simplify 7 over 6 and turn it into a decimal. Just leave it there for now, right? We'll get it in the end. And then how does the left side simplify? You're just going to get the exponent, right? Whatever there, that's what it is. So we're going to go up here. T plus 5 equals log base 2 of 7 over 6. Now this is the step that after you did take the log of both sides, it's possible there's a little bit more left to do to solve for the variable. In this case, you got to subtract 5. So we'll go t equals log base 2 of 7 over 6 minus 5. So I'm going to turn that into I'll use a change of base. T equals log of 7/6 divided by the log of 2 minus 5. And that you could put in the calculator. Log of 7 divided by 6 divided by log of 2 minus 5. Negative 4.7776 T equals negative 4.778. The directions for these all said round to 3 decimal places, so that's why I'm doing 3. I'm not sure why, but it is true that when you get to calculus and you got to do everything for the AP exam always says 3 decimal places. Now, if at this step right here, if you have an 84 or better, and you've got the log base function and you just put it in like that, that's fine. I mean, remember that in class, if you're using that class set, you have that option. Remember the math, scroll to the bottom, log base, right? So you can actually just put it in the calculator that way. If you were issued an 83, which a lot of you were, then you can't do that at home. You got to use change of base. Okay, logarithms. So we did the standard procedures to solve an exponential. Now the standard procedures to solve a logarithm. First step, as always, isolate. What do I have to do to isolate this? Subtract 7. 3 ln of x equals negative 2. Then divided by 3 ln of x equals negative 2/3. Okay, now go back to the directions. What did I say to do after? After you isolate for a logarithm. Convert to an exponential, right? That's something we did 2 sections ago. We know how we convert logarithms to exponentials, right? You take the base of the logarithm is the base of the exponential, so it's e, right? The logarithm equals the exponent, negative 2/3. And then what's inside the logarithm goes there. So e to the negative 2/3 equals x. And that's something you can put in the calculator, right? And notice that on your calculator, if you look above the ln, it says e to the x. So you could actually just hit that button. And it puts you in the exponent, negative 2 divided by 3. 0.5134 x equals 0.513. Now, if you look in the book, it probably doesn't say that exactly, right? What they say at that step is they say, it's like when we say for exponentials, take the log of both sides. Well, then at this step, it'd be take the exponential of both sides. They don't say it exactly like that. Say exponentiate both sides. By exponentiate, what they mean is, if ln of x equals negative 2/3, then pretend like, not pretend, but we're gonna make those the exponents of e, right? We'll do that to both sides, so it's equal. Now we've got e to the ln of x on the left and e to the negative 2/3 on the right. Well, e to the ln cancels each other out, just like ln of e cancels each other out, right? That's the difference between f of f minus 1 or f minus 1 of f. It doesn't matter the order, they will cancel each other out. So we just get x equals e to the negative 2/3. I used to always do it like that myself. But I never liked the fact that when you write things not as exponents, you write them a little bigger, right? When you think you're putting something in the exponent, you usually write it smaller. So then I end up with these, and I try to make exponents out of them, And I want to draw the e to make it bigger so it makes this look like it could be an exponent of it. And the truth is, it's kind of messy and hard to see, and you get the same result if you just convert it to an exponential, right? If you just say, where were we? E to the negative 2/3 is x, done. And that's something we should know how to do by that point. Okay. What do I need to do on this one? Divide by 3. Right. And remember, whatever's inside the logarithm, right, you can't mess with that because it's inside the logarithm. So this divide by 3 doesn't change the 6x. Right? Log base 4 of 6x equals 3. Okay, now that we've isolated it, convert to an exponential. What will the exponential be? Here's the base, 4 to the 3rd equals 6x. Okay? 4 to the 3rd equals 6x. Again, that's that next step. There could be a little bit of solving to do at that point. I mean, in this case, it's not much, but there is another step to take. Right? 4 to the 3rd is 64. X equals 64 over 6. And you could simplify that as a fraction, but we're turning everything into decimals anyway. So 10.666 repeating. So I got 2 more examples here. You okay, Hannah? Okay, so these are kind of along the lines of exceptions, right? I said that there's some that you can use the basic procedures, like I just said. This is a little bit different than that. I mean, if you said first it's a logarithmic equation, so isolate the logarithm. Well, there's 3 logarithms. So how are we going to isolate the logarithm? We're not. What we're going to do is we're going to turn it into a one-to-one property. Let's use our properties of logarithms to make the left-hand side one logarithm. And then we'll have one logarithm equals another logarithm, and then use one-to-one property. Right? What property would I use to combine these two? Log of 4x minus log of 12 plus x. It's a quotient property, right? So you put them together into one logarithm using a quotient property. Log of 4x over 12 plus x equals log of 2. Okay, now if the logarithm on the left equals the logarithm on the right, then use the one-to-one property. That means what's inside has to be the same. Right? These two are the same. 4x over 12 plus x equals 2. 1 to 1. And now that's something you should be able to solve. If you have trouble with something like that, think of it as a cross multiply. Right, you can put that over 1, cross multiply. We'll get 4x equals 2 times 12 plus x. 4x equals 24 plus 2x. 2x equals 24. X equals 12. Right. This is exactly the kind of situation there. You got to take that last step too. Then what did I say was the last step for logarithms that you don't have to do for exponentials? Yeah, check for extraneous. Make sure that this 12, when you put it in here, there, and there, that it would not lead to the logarithm of a negative number or 0. Let's see, if I put in a 12, 4 times 12, 48, that's positive. 12 plus 12, it's 24, that's positive, so that'll work. No extraneous. We're good with that? Okay, one more. Uno más. Okay. So what do you think we'll do to start this one? Based on what we did on the last one, you can use a product property to combine into one, right? When we do that, what it's going to look like, it'll be log of x times x minus 9 equals 1. Now, that's not a one-to-one because we don't have a logarithm on the other side. So instead, do what we do, right? We've isolated a logarithm. The next step says convert it to an exponential. What's the base of the logarithm? It's 10, right? So this is going to be 10 to the first equals x times x minus 9. Right, so let's simplify on the left. X squared minus 9x equals 10. And you in your mind, you got to be thinking, okay, it's kind of quadratic. I got to solve it like a quadratic, which means in almost every case, I need to get everything on one side, 0 on the other, and then I can figure out whether it's factorable or whether I can use a quadratic formula or whatever. In this case, when I subtract, I get x squared minus 9x minus 10 equals 0. Right, that's a simple quadratic. Are there any factors of negative 10 that add up to negative 9? Negative 10, positive 1, right? So yeah, there are. So it's factorable. So you don't want to use quadratic formula if you don't have to. Right? That's going to tell us that x minus 10 times x plus 1 equals 0. So x equals 10 and negative 1. Okay, now we got to check. Right? If I plug in 10, right? If I put log of 10 plus the log of 10 minus 9 equals 1, I mean, that's going to be log 10 plus log of 1 equals 1. I mean, there's no domain problem, right? I'm not going to throw it out because of domain. So this one is checks. Check. Now let's check the negative 1. If I put in negative 1 for x, then I'll get log of negative 1 plus the log of negative 1 minus 9 equals 1, right? In both of those, you're taking the log of a negative number. You can't do that, right? It's not in the domain, so you have to throw it out. That's extraneous. That's what extraneous looks like in a problem like this. You get down to the end, you throw it back in there, and you find a domain problem. So that means not a solution. Easy. Not too bad. So we did, right? The simple equations, I meant one-to-one. The rest of them are not one-to-one. Did some pretty concise directions there. When you're going over them, right? pull up those directions and try to follow them. Isolate. Take log of both sides. Convert to exponential.